Now that we have the moment of inertia, we have the moment, and we have the neutral axis position, we will be able to solve, basically find the stress at any layer at any point on the beam. Okay. So here, of course, based on the assumptions, right? So sigma equals my over I, it has its assumptions, right? The linear behavior of the beam in that part, basically, the homogeneous properties are the same, and the plane sections remain plane, and all the other stuff we can find in theoretics. We assume that this formula, of course, applies, right? So here, sigma equals my over I. How can we apply it? It says, the question says, find the maximum stress at a layer located just above the circular hole. When it says maximum stress at a layer just located below circular hole, this maximum here means that take the maximum moment, right? So we're concerned with the maximum moment in the beam. And then here it says, now here it defines the layer. If it does not define the layer, you automatically go to the top fiber and the bottom fiber and compare to see which one is higher. Because as we know, moment is the largest at the edges, right? At the top fiber or the bottom fiber, just naturally. And in the neutral axis, our moment is going to be 0. Basically opposite to the shear, right? Because for shear, at the edges, you don't have any shear, right? Because shear is not defined. Shear is a contact of two surfaces. Here as well, shear is 0. And in the neutral axis, you have the maximum shear, right? You can think of moment and shear as complementary. Force is distributed in a way of shear and basically normal force, right? Or moment in this case. So here, we have this formula. How do we find it? We have this from the diagram. The maximum moment we saw was 130. And moment of inertia, we found it before. The only thing we don't know is y. Well, we can say that we want to find the y. What is y? Y is the distance from the neutral axis. Always. It doesn't matter, where we're dealing with. So y is the distance from the neutral axis to whichever layer that we're considering to calculate our stress at. So in this case, let's say we want to find the stress at the bottom fiber. We'll say y is equal to the distance from neutral axis to the bottom fiber, which is 47.2. What about the distance, let's say at the top fiber, is the distance from the neutral axis to the top fiber, or basically 700 minus 47.2, this distance. The question in this case asks us about the circular hole only, above the circular hole. So we want to find the maximum stress at this layer. Okay? So we need to know what? We need to know the distance from neutral axis to this layer. What is this? Well, to find that, we need to also know this one. What is this? Well, this is 200 minus 75, right? So 200 minus 75, which is the diameter, gives us this one plus this one. So we just divide by 2 to only get this one, right? Easy as that. 200 minus 75, divide by 2. So it's 62.5. So basically, what is this? It's going to be 700, the whole thing, minus 47.2, minus 62.5, you get this one. So that is our y, and that's it, right? That we know the formula. Sigma above circular layer is moment times y that we just found, divide by I, right? My over I. Simple. A very important point here. Whenever I want to calculate my sigma, I always use Newton and millimeters. Why is that? Because the most common way of reporting stress values is megapascal. And if you use Newton and millimeters, you will basically end up with megapascal automatically, because Newton per millimeter squared is megapascal. So whenever you write this, it's better to convert all your units to Newton millimeters. For example, you had 130 kilonewton meters. You can just say 130 kilonewton meters times 10 to the power 6. That is Newton millimeters, right? So if you multiply this number by 10 to the power 6, you'll deal with Newton millimeters. And these are basic unit conversions. You probably know it much better by now, right? So here, this is y, this is millimeters, and this is I, millimeter to the power 4. See, all units are Newton and millimeters. Easy. So here, based on this, we calculate this one, and we end up with this number, 3.062 megapascal already, right? So again, remember the number that you get here is this, and will be megapascal. No need for further conversion. So that's the answer for question 3. So let's go to question 4. It says determine the maximum tension and compression forces and find the resisting moment based on average stress values. So this is very important. In this question, it says find the maximum tension and compression forces. Maximum. So if you remember, we found the stress at this layer, right? But is that the one that we need here? Not really, right? Because we are dealing with the forces, total forces that exist. So what we need to do is to find the stresses both at the top layer and the bottom layer, right? To make our job easy, right? Because why? Because we need to draw our stress diagrams here, right? And in order to draw the stress diagrams, we need the maximum value here, we need the maximum value here, right? The middle values are no good to us, right? We don't care about those. And after, of course, drawing those stress diagrams, we can take an average value, multiply by the corresponding areas, and based on that, we can find the compression forces and the tension forces. Let's see how it goes. Sigma top fiber, how do we do? So here, 130 times, again, like the exact same thing we did in the previous page for the, like above the circular layer. You see the moment is the same, the moment of inertia is the same. The only difference is y, right? Y is going to be, again, the distance from neutral axis to the top fiber. It's going to be 700, the whole thing, minus 407.2, right? Simple as that. And here this is the number. And for the bottom fiber, we have this moment, and we have this y, and we have this moment of inertia, right? Again, this y is distance from the bottom line, again, this is from neutral axis to the bottom fiber. So these are our stress values, okay? Now, based on these stress values, we are now prepared to draw our stress diagram. So here, what is the stress diagram? It's going to be something like this, right? And we will see it later. But before that, remember the moment is negative for our case. And why do we need to know this? This is very, very important. If you go back to our moment diagram, you can see that the value that we had was negative 130, right? The maximum value, negative 130. It was negative. What does negative moment mean? This is negative moment. Negative moment is basically in the direction of compression at the bottom, tension at the top. That's what negative moments mean. And positive moment means like the opposite, right? This is a positive moment. So if you're dealing with negative moment, then let's say this is a ruler, how is this going to bend? It's going to bend compression and tension like that, okay? So compression at the bottom, tension at the top. Easy as that, okay? And why do we need to know that? Well, because when we're drawing our stress diagram, our arrows, here I didn't draw any arrows, but you can know that, okay, tension, which means that it's going to be pulling here, right? These arrows are to the right, and these arrows are to the left, okay? Because these are pushing in, and these are pulling out, okay? Tension at the top, compression at the bottom, simple, okay? So that's basically what means. For example, if your moment is positive, auto area, right? So let's say our moment was negative. This is our stress diagram, and our total tension and compression forces will look like this, okay? Total tension force, total compression force, okay? How do we find these values, okay? Of course, I talked about this point extensively. Of course, we're dealing only with point D here because we're talking about maximum, okay? So we deal with the maximum moment that we had, right? So that's why these all represent point D, which is the maximum moment, right? So let's now go find the tension force and the compression force. How do we find the tension and compression forces? Basically, what we can do is just say, what is a force? Force, and forget about this average for now. Force is equal to stress times area. Simple, right? We know stress is equal to force over area, and so force is equal to stress times area. But in this case, that just doesn't like work like simply, right? We just have to assume some stuff. How can we do that? Well, what we can do, just an approximation, right? We say, you know what? This is the area that corresponds to this force, right? Which is basically the tension force, right? The whole area above this neutral axis is under tension, the whole area. And the whole area below it is under compression, right? Based on the principles that we studied. So we have to basically, this is the area that we have, right? For this, the tension area, AT. And the sigma T average is going to be something, basically the stress here, right? Is going to be a stress value that represents the whole area. I would say, you know what, just a simple calculation would be, well, so you know what, just take an average here. Let's say that for this whole part, for the whole area, my stress varies from 0 to 3.893. So what I'll do is just take a value that represents the whole section, right? It doesn't mean it's true, right? But it is a fairly good approximation, right? To just see, okay, that, you know, just take a value that represents the whole points, right? It represents this point, 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 right? On average. And what is the best value for that? Oh, we'll say, you know what? We can just take the average, right? So 0 plus 3.893 divided by 2. Simple as that. So we'll just say that this value is 3.893 divided by 2, and AT is the area above this. But how do we find this AT? We have to section, right? In other words, we have to just divide it into different pieces. We say this is piece 1, piece 2, piece 3, the whole rectangle, and piece 4 is this circular hole, right? That's the area, right? Again, remember, the concept is force is equal to stress multiplied by area. For stress, we took an average value that represents the whole section, the whole tension area. And for area, we just simply are calculating the area above the neutral axis, which is under tension, right? That's our concern. So for FD, so this is what I mentioned, AT, what is AT? Is the whole area, right? A1, A2, A3, minus A4, right? Because it's a whole. How do we calculate that? Simple, right? Again, this is 200 multiplied by this value. What is this value? Well, you can calculate it again based on this. So 292.8 minus 200, right? It's going to be this value, right? So 200 times 92.9, and then we have 200 again times 92.9, and or probably this is 92.8. Yeah, so it might be a typo here, 92.8. It doesn't make much difference here. You have this for 3, you have this 500 multiplied by 200 minus the area of the circle, which is pi times 75 squared over 4. But it is a simple area calculation, the area of this plus the area of this plus the area of this minus the area of this circle, right? Simple. Now you have this AT, you have this one, and you can easily calculate your tension force, right? Remember, your area you found is millimeters squared. The stress that you got is in megapascal or Newton per millimeter squared. So the answer you'll get for your force is in newtons. So the only thing I did was just multiply at the end by 10 to the power of negative 3 to get it in kilonewton. Simple as that. So this is our tension force, right? Same idea for compression. For compression, again, the same thing. We say 5.414 plus 0 divided by 2 to be an average stress for compression area. And the compression area, we say this is section 1, like segment 1, 2, 3, 4, and 5. We add all of these areas together, right? And you can see the calculation here, right? For example, again, for section 3, what is the area? 300 times 100. Simple, right? And then we add them together. And finally, we multiply the average stress multiplied by area. This is going to be your number, okay? And again, if you multiply this by this, you won't get this number exactly, right? You're going to get this number multiplied by 10 to the power of 3. Why? Because your number will be in Newton. But I want my number in kilonewton because it's, you know, simpler, you know, more common. So I'll just report it in kilonewton, okay? So your tension force is this much, your compression force is this much. Now we need to find the resisting moment based on the average stress values. How can we do that? Well, we have the forces, tension force, compression force, right? We can easily calculate the moment, right? Resisting moment. How? We can say, you know what? Just take the moment of these two forces about the neutral axis, right? You can, by the way, take the moment about any point, right? But taking it about the neutral axis just makes it more accurate, right? Because here we have, you know, we have had, you know, we can have like some round off errors and things like that. So here we take the moment about this one and this point, and we'll have, of course, we know these, right? These are known data. So based on those, we'll say that what is the moment that this creates about this point, and what is the moment that this creates about this point? And we know it simply, right? So Ft will be multiplied by this distance plus FC multiplied by this distance. But what is this distance? We can see, right, this is a rectangle, this is a triangle, right? So the equivalent force will be located here, right? A third from the edge. So if this is a third from the edge, this is 2/3 from the edge, right? So if this is 292.8, this is 2/3 times 292.8. And this is 2/3 times 47.2, right? So simply Ft times this value plus Fc times this value, okay? Simple as that. And based on that, we get the final number as this much kilonewton millimeter, right? Or 95.01 kilonewton meter. Simple. Okay, that's our resisting moment. But so wait a minute. Our applied moment was, before even going there, our applied moment was 130, remember? But this is 95.01. Why aren't they the same? But like the resisting moment should be equal to the applied moment, right? In this area. Well, the reason is that we basically made some assumptions, and that those assumptions were not accurate, right? They are just an approximation, right? So that's why 95.01 is not equal to 130, okay? And of course, the same as tension force and compression force. These two forces also equal, right? And you can think about the reason as well, right? So for example, here you see we have like this much like large stresses, which represent like a large area, see? But what value we took is like around this value, right? But you see like larger stresses exist here, right? Simple as that. Or for example, for this one, probably we took like a value like this, which might exaggerate because these values like for smaller, again, like you can think about it that way as well. But again, that's the reason behind why they are not equal. And for the fifth question, it says write the shear force and bending moment equations for portion CD with B as the origin. First thing first, when it says B as the origin, right? If you remember, when you cut a section, you will have an X value, right? That X value is going to be from the origin to wherever you cut. Simple as that. You should remember this sentence. From the origin to wherever you cut is your X, and you'll see it later. So when it says write the shear force and bending moment equations for portion CD, you cut it like at an arbitrary point between C and D, and you either take the left side and you take the right side, right? Either. In this question, we're going to do both. So first, let's do with the simpler option, or not the simpler option, the option that many people will go with, because like it's convenient to probably take it to the left side for some reason. But you'll see that taking the right side is much simpler in this case as well. So, just look at the question and see which side is easier, that's all. So let's first start with taking the left side, right, like that. When you cut a section, you'll have shear moment and axial force we're neglecting. Shear is, in this case, as we know, conventionally, your shear is going clockwise direction. Moment is in the direction of compression at the top, right? And again, you don't have to remember that because I'm going to do like both of them. So just remember these. When you take the left side, your shear and moment is going to look like this, okay? In terms of direction. And so basically, when we do this, we have to know what X is. We have to know what other dimensions are. Other dimensions are given, so we just, again, whatever dimension we know, we just put it here. But what is X again? It's from the origin to wherever we cut. So this is X. Simple. Now what we do, first of all, is also say, what is X applicable to? What is the range of X? Well, we say, okay, you say that the question says, origin is B, and I want to write the equation from C to D. So if origin is B, so it's up from 0, and we go forward, now we're at 5, and then we're forward, and this is 10. So what does it mean? It means that we are writing an equation from C to D. It means that our X is applicable from C to D, or from 5 to 10. That's all. Simple as that, right? So now that we know this, we just have to take the moment about any point and find the moment, this M, right? We're trying to find M and V as a function of X. But again, if you remember, I mentioned something before. Take the moment always about where you cut. That is very, very important. Take the moment about wherever you cut. So in this case, we're going to take the moment about point O. Simple. Okay. So here, and that's only just to make things easy. That's all. Okay. If you do it like another way, you'll see what I mean. Right? You have to deal with shear. You have to find shear first. Sometimes you don't need the shear. In this case, you do need the shear as well. But that's just extra head. Extra headache. You don't need that now. So you take the moment about point O. The summation of 0. Have a convention. Let's again start from the left. We've done this before as well. So 10 times 6 divided by 2, the magnitude, multiplied by the lever arm. What is the lever arm? So first of all, the magnitude. Magnitude is 10 times 6 divided by 2. We know this. What is the lever arm? This is the total magnitude, right? This is 4, remember? And this is x, right? The lever arm is x plus 4, right? Simple. And then you have the 69 kilonewton load, right? And by the way, what was it? Is a positive or negative? So it's turning it this direction, right? For this triangular load. It's this direction. It's positive or negative? It's positive. There you go. Then you move to this reaction. 69 kilonewton multiplied by this x, right? Is it negative or positive? Well, turning it in the clockwise direction, so negative. There you go. And then the distributed load. 5 times x, that's the magnitude, multiplied by x over 2, that is the lever arm, right? So it's going to be 5 times x over 2. And is it positive or negative? It's going to be positive, right? Turning in this direction. Remember again, we're taking the moment about point O. So this is like your pin here. You can consider this as a pin, right? This is a ruler, and you just put your hand, put your finger here, and you apply other loads with your other hand. In what direction is it going to turn? That's how we determine what the direction is. Negative or positive. And finally, we have this load, 30 kilonewton load, 30 multiplied by this lever arm. What is this lever arm? X minus 5, right? From here to here is x minus 5. So 30 times x minus 5, positive or negative, it's going to be in this direction, so it's positive, based on the convention. So summation is 0. I will keep m here on the left side, bring everything to the right side, right? And based on that, after simplification, I will end up with this equation. And by the way, you can check your equation here, this one. You can check this with the moment diagram that you have, right? Because it's exactly the same thing. So from portion C to D, you can give values. For example, for C, you're going to give 5, right? Because as we know, x is applicable from 5 to 10 based on the origin that we have for B. For C, you can put 5 here, put 5, and you can put again 10 here, 10, 10, right here, 10, 10, and find the value. You'll see that your moment diagram is going to be exactly the same value. That's how you can check as well. And for the shear diagram, you just take the summation of the forces in the upper direction, in the vertical direction basically, and upper direction is my positive. So again, it's pretty simple. Just, each force, 10 times 6 divided by 2. For this one is 5 times x, right? And of course, going down is negative, so negative, this is negative, minus 30 going down, by positive 69, minus v, right, it's going down, minus v, and it's going to be 0, right? Of course, I think I forgot about like this m, right? Of course, always remember to include your m in your equation, right? This is m plus m, right? Because I forgot to say it, I think. So yeah, after you deal with all of your loads, include this m as well. But remember, always take your moment about this section, like this point wherever you cut. Because sometimes when you don't, you forget about this v, right? And here I did not include v because I'm taking my moment about point O. So v goes through O, so the moment is 0, resulting from v. So you don't have to deal with that. But if you take, like, let's say your moment about this point, you have to consider v as well, meaning that you have to first find v and then write this equation. Okay, so you see, like, that's the complication. So always take the moment about where you cut. That's very important. And again, after solving this equation, you can find your shear equation, and again, you can check it from your shear force diagram. That was taking the left side. Now let's do it the easier way. Let's take the right side. Why is it easier? Because first of all, I'm dealing with simpler forces. I'm not dealing with a triangular load. I have less forces here, right? Fewer forces. And It's going to be easier. So let's see. I'm going to take the right side. Again, this is the convention. If you take the right side, V is going to be upward. Moment is going to be, again, compression at the top. So based on this, again, X is applicable from 5 to 10. Nothing changes, right? Again, as I said, no matter if you take left side, right side, your X is going to be from the origin to wherever you cut. From here to here. That's your X. The only complication that you have for taking the right side is that what is this dimension? So we know this is 1, this is 3. What is this? Well, pretty simple. If from here to here is X, right? As we know. What is from here to here? 10 minus X. Why? Because this is 10. And if you consider it from here to here as X, so this is going to be 10 minus X. Simple as that. Right? And that's it. That's the only probably difficulty that you deal with this one. So again, take a moment about where you cut. Same ideas apply, right? So I'll just let you, go through this and see how it goes, right? For example, just an example. Let's say, for example, for this 5 kilonewton per meter force. I'm taking a moment about this one. 5 kilonewton times 10 minus X. That's the magnitude. There you go. 5 times 10 minus X. Times the lever arm is from here to here. 10 minus X to over 2. Right? Negative or positive? Well, it is in this direction. It's going to be negative. Why? Because it's clockwise. Negative. My moment, what is it? Is it negative or positive? Well, it is negative. Why? It's clockwise. Minus it. Right? And all the same things for the other ones, right? So you can practice it and you'll see that it's a little bit easier and you'll end up with that value. Same for shear. And that's your shear value. Okay? And that is for question 5. And for question 6, it says consider that the strain at the top fiber just to the left of point B is 150 micrometer per meter. So at this point, at the top fiber, right, the top of the cross section, we have installed a gauge, a strain gauge, and the value we had was 150. And we'll say, okay, if that is the case, what is this actual load that we've had here? What is it? Well, we'll say that, so let's see, what is, so we have a strain and you want intensity? How can I know that? By the way, the marginal elasticity of timber is also given as 15 GPa. Well, there's a way, if you think about it, right? How is strain related to force? Well, first of all, we know from Hooke's law, strain is related to stress, right? And then we say, okay, stress, do you remember the stress formula? Sigma equals my over I. Yes, we do. So sigma is also basically relevant to m, moment. In other words, if I know my moment here at point B, just to the left of B, do I know my W? I do, right? Because I can just take the moment about point B and find this W. Simple as that. So let's see how it goes. I have my stress. This is the Hooke's law. E, marginal velocity times strain. So here I want to find a stress. So stress is equal to 15 times 10 to the power of 9. So this is marginal velocity. This is gigapascal. And this is 150 micrometer per meter. 150 times 10 to the power of negative 6. Micro is 10 to the power of negative 6. This is going to be equal to 2.25 megapascal, right? No need for conversion. Newton per, actually you have to convert as well. Newton per meter squared, you have to convert it, right? So you have to just multiply at the end by 10 to the power of negative 6 to get it in megapascal. Then you have this formula, as I mentioned, sigma equals my over I. What is m? Just basically change the positions here. Sigma times I over y is going to be your m, right? So sigma, what did we find? 2.25 megapascal. I, we know it from before. Y, again, what are we evaluating? We are evaluating the top fiber. So what is y? Y is the distance from the neutral axis to the top fiber. Okay, so 700 minus 47.2. Again, you see everything is in megapascal, millimeter, Newton. And at the end, we'll end up with an m value of 75.129 kilonewton meter. Remember, the value that you get from this, solving this one, from basically finding the value, it's going to be 75.129 times 10 to the power of 6 Newton millimeters. And then you convert it to kilonewton meters. Okay? Now that we have the moment, what does it mean? it means that you have the moment just to the left of B here. That's your moment. You have this M. It's like cutting a section. If you cut a section, you know this M value. So if you take the moment about O, you get rid of the effect of V as well, right? So we don't have to know V anyways. If you take the moment about this, you have one unknown, one equation, because you know M. So it will be W times 6 times 1 over 2 times 4. W times 6 times 1 over 2. That's the total force, multiplied by the lever arm, which is 4. That is equal to 75.129. So from here, you can find W. Simple as that. Some people might say, wait a minute, how is it possible? How does your directions work? This is counterclockwise. This is counterclockwise as well, about point O. Well, the point is, yeah, I did draw like this M as counterclockwise based on the conventions we've had. But as you remember, M is always negative, right? Consider this. This is a overhang. So of course M is going to be negative, right? So M, the value that you have is actually negative 75.129, but we don't care about that, right? This is a simple case, right? This is your load, right? If your applied load is here, like this, in this direction, your resistance is obviously going to be in the other direction, right? It's resisting in this case. So this is just a formality, just writing it based on the convention that we know in order to be consistent with our moment diagrams when we cut sections. But obviously when you have a force like this here, in an overhang, applying in this direction, your resistance is going to be in the other direction, like that, at point B, okay? So you don't have to be concerned about that, okay? So you just put the values, and your W might be negative, doesn't matter. You know what you're dealing with. As long as you know what you see, you'll be fine. And that's your W. And finally, the final question is, let's say a hollow rectangular section made up of these pieces. So we have 100 millimeter times 300 millimeter pieces. So these are the pieces you see. Again, this is another piece, another piece, another piece. These are glued together or nailed together. Doesn't matter. That's not the concern of this question. It says now, in this case, find the factor of safety if the flexural capacity of timber is 10 megapascal. So, factor of safety. How do you find factor of safety? Well, factor of safety is applied stress in this case, right? Applied stress over the allowable stress. Actually, sorry, allowable stress over applied stress. That's going to be factor of safety, right? So, basically, at the end of the day, we have to find the stress, right? We know the applied stress, and basically we know the allowable stress, 10 megapascal, given in the question. We have to find the applied stress in order to find the factor of safety. What is the applied stress? Well, this is basically another question, right? We're not dealing with the previous section, right? So this is a new section, and we have to find sigma equals M by over I. What is M? Well, it's the same beam, right? We're just using a different cross section, so M is known as 130 kilonewton per meter. Y max is going to be 200 millimeters, right? Because we want to see the maximum stress applied to the section, right? So what is Y? The maximum is going to be always, as I said, the top fiber or the bottom fiber. The maximum is 200 millimeters, okay? And I is going to be like this. Again, you can consider this as a rectangle. So it's going to be 400 times the moment of inertia, basically, again, like it's the moment of inertia of this large rectangle or square minus this small square, right? Moment of inertia of this large one is 400 times 400 to the power of 3 over 4 over 12, or 400 to the power of 4 over 12, right? Like this, minus the smaller one, which is 200 to the power of 4 minus 12. So from here, you get this I value. Your applied stress, again, this is like we did it multiple times, moment times Y over I. From here, you'll end up with 13 megapascal, and your factor of safety will be, again, as I mentioned, allowed stress over the applied stress. Allowed is given as 10 here. Applied here, as you found 13, it means that it will not be safe, right? It will not be safe. But if you remember, what was the stress that we used from the previous section for the main original section we had? The maximum stress was in the bottom, right? The bottom fiber, if you remember, it was 5 point something, right? 5.5, 5.6. And that was safe, right? So for that one, the factor of safety is 10 over 5.6, around 2, right? Factor of safety is 2. So that section is safe, right? Although a little bit complicated. But see, this section is not. And what's the reason? You see, like in terms of height, this is only 400 millimeters, right? We're basically wasting the section in terms of lateral, basically resistance, right? Again, like we're not concerned in this case about wind, right? That's another discussion. But the only thing we can say is that the stiffness or the momentum of inertia about the major axis is not sufficient for resisting the flexural stress for particularly this section, right? This is not enough for the beam that we have. And that's it. So that's the final question, and the section is not safe. Thank you for watching the video. If you enjoyed the video, please like and subscribe down below, and subscribe for more content about problem solving in structural engineering. Also check out the other videos that we have for strength of materials. We have a full collection of strength of materials concepts, at least about the second part of strength of materials, basically not concerning statics. So you can check out those videos, and I'll see you later.